Well, we probably ought to get started. Just a reminder, we've got mid-semester grades are coming up on the 19th of October. So if you have any late assignments due and they're not due before that date, I have time to grade them, then I'll have to enter a 0 for those late assignments. But after midterms, if you turn the assignments in late, there's no penalty. I'll just grade them and update your average. But a low grade at midterm, you know, might precipitate some action from administration. I don't know. They might get involved, but just know that your overall grade won't suffer as long as you turn things in before the end of the semester. Okay, I think some others showed up. Yeah, there's Justice. And I bet I can find Jeannie. Yep. Okay, that's everybody. So we can get started on the next topic if there are no issues that need to be dealt with at the present time. Okay. I might take this. I was kind of chilly there for a while, so I put my lab coat on. Now I don't think I need it. So I'll give it to one of the cats. Let's see, am I recording? Yes. All right. So now we're, our next chapter topic is thermochemistry. So let me share the, PowerPoints. And start the slideshow. If I can find it, there it is. There we go. Okay, if I don't hear from anybody, I assume that you can all see the slideshow on thermochemistry. It's not likely that we're going to finish this introductory material today. We'll have to finish it on Thursday, I'm pretty sure, because there are some topics that we get into, and I want to be sure that I present them thoroughly. So if I'm lucky, I'll get halfway through and we'll finish it up on Thursday. And then that'll leave the following Tuesday for review. Thermochemistry. Well, we ought to have a pretty good idea of what chemistry is by now. Thermochemistry is the study of heat transfers that occur during chemical reactions. And we probably have to get some definitions under our belt first. One is energy in particular. Energy and heat are not synonymous. In fact, heat is a form of energy. In fact, heat is only measured by a transfer from one place to another. In other words, you can't measure heat as an intrinsic value. So what is energy? Well, energy is anything that imparts the capacity to do work or to produce heat. So energy can, ideally, if you're trying to make the most of the energy that's available, you want to do the maximum amount of work. And I'll define work for you in a minute also, because there's a strict physical definition of work as well. But whatever is not converted into useful work ends up as heat. The overarching law that encompasses energy is the law of conservation of energy. And it just says simply that you can't create energy, you can't destroy energy. All you can do is transfer it from one place to another. Now this, another way of stating it is that the total energy content of the universe is constant. And that is, in its simplest form, a statement of the first law of thermodynamics. And we're not going to jump into the laws of thermodynamics right now. I'm just telling you that's what it is. So when we get to entropy, well, I don't think, not this semester. Entropy is in the second semester. But when we talk about entropy, then we'll introduce the other laws of thermodynamics. But this is the first one, and this is the one that's the focus entirely of this chapter. It has to do with energy conversions during chemical reactions. It's very rare that you'll find any chemical or physical process that does not involve the transfer of energy. They almost all do in some form or fashion. Any process that you identify, whether it's chemical or physical, involves a transfer of energy of some sort. Okay, we can also divide energy into two categories. It's either potential energy, and that's potential energy is due to one of two, not causes, but it can be defined in terms of either position, and that the best example of that is height above the center of a large mass like the Earth. And we call that gravitational, also call that gravitational potential energy due to position. And anybody who's ever climbed up a ladder and fell off knows what that is. You have to expend energy to go up the ladder, and if you fall, when you hit the ground, all that energy that you put into that climb is released against your body when you hit the ground. So you're storing up energy based on your position in a gravitational field. Other types of potential energy, it could be due to composition. We all know that some chemical compounds have the ability to release enormous amounts of energy, such as nitroglycerin, or TNT, trinitrotoluene, any of the explosives, or AMFO, which is ANFO actually, ammonium nitrate fuel oil, which is a mixture that's used commonly in the mining industry to boost the explosive force of the charges that are placed in certain, well, in drill holes. Let's just put it that way. Drill a hole, stick a stick of dynamite in the bottom of it, or TNT, or whatever you have available, and then you overpack it with ANFO. And the chemical reaction of fuel oil and ammonium nitrate boosts the value of that stick of dynamite by several orders of magnitude. So how did it do that? Well, there's energy stored in the molecules, and the chemical reaction releases that energy. Other forms of energy due to composition may have simply to do with electrostatic attraction or repulsion. You all know that if you take two magnets and you turn the poles, same poles together, they'll repel one another. And you can hold them there for a little while, but if you release the force on those magnets, they'll fly apart. You've stored up potential energy based on their, well, I guess you could argue position, but on the molecular scale or on the atomic scale, you've stored it up in the composition, the position of the composition, so that the things get kind of mixed up here in a salad bowl. So that's potential energy. It has the ability to do work. But kinetic energy also has the ability to do work, but it's due not to any potential that's there, but to actual physical, measurable energy due to motion. If something is moving, it has kinetic energy because everything has mass. So if it's in motion, it has kinetic energy. And it does depend on two things: the mass of the object and how fast it's going. And that also includes temperature. Things that are warm to the touch, say, they have kinetic energy as well, because the individual atoms or molecules inside that substance are in motion. And the faster they move, the more kinetic energy they have, and the higher the ability of their transfer of heat to your hand when you touch them. So if you heat up your cooktop on your stove and you don't wait for it to cool down, you touch it, you find out that, yeah, those molecules have kinetic energy, and they have enough to burn the skin off your fingers. So how do we calculate it? For every individual mass, you can calculate a kinetic energy based on 1/2 of its mass times the square of its velocity. And that's the kinetic energy formula for any moving object. Now we could talk about units, and we probably should. What are the units of energy? Well, we already know that the units of energy are joules, right? So if kinetic energy is equal to 1/2 mass times velocity squared, then what's the equivalent to joules in the SI system? Well, mass is in kilograms, velocity is in meters per second, so you square that, and joules then is equal to, the units are equal to kilogram meters squared per second squared. So that's the advantage of the SI system. Everything is convertible, and you can derive lots of different units of measure once you know the fundamentals. And kilograms, meters, and second are all fundamental units. Joules is a derived unit because it can be broken down into fundamentals. Okay, so we can divide energy into potential or kinetic energy based on whether it has the ability to do work or it actually has energy of motion. Okay, so when energy is transferred on its very simplest level, two particles represented by these balls, one, A, has a higher potential energy than B because it is higher in position. And we're assuming that down on this slide is toward the center of the Earth. So the gravitational field allows us to move that A up to a certain level, and it's supposed to be at the level of this other side over here. Right? Sort of an optical illusion, but A is at this high level, and if we release A and let it strike B, and if the collision is completely elastic, then all of the energy of A will be transferred to B, and theoretically, B should roll up to the top because now it should possess the same energy that A had before. And of course, when it starts moving, it has kinetic energy that's equal to A's potential energy. But then as it travels up the slope, it converts that kinetic energy into potential energy of position. So let's see what happens. All right, so A struck B, and B only made it up to the first level, this flat spot. Okay, why is that? Well, we can't create energy, we can't destroy energy, so the energy that A had was transferred to B, but now B says it only has this much energy. So where did the rest of the energy goes? We can't create it, we can't destroy it, so we have to account for it. And the energy that we can't account for yet, we know is due to friction. In other words, the rubbing the balls as they roll on this surface has robbed B of some of its energy. In fact, as A dropped, it lost some energy before it even hit B. So that lost energy is due to frictional heating. You know, when you rub two things together, right? My hand's going to get hot. That's friction. And we can account for the energy lost as friction. Okay. Now let's pause for a second, because it's real easy to equate temperature and heat. They're related to one another. I don't deny that, but they are different measurements and different quantities. Temperature is an intensive property. Remember what intensive is. If you measure the temperature of a substance in one spot and you claim that that substance has the same temperature throughout, it's at the same, I'm going to introduce a concept here. Let me hold that for a second. As an intensive property, you can measure the temperature anywhere in that substance and it's always the same. And temperature, in fact, is a way of measuring the random motion of the molecules in a substance. In fact, in more exacting terms, temperature is proportional to the average kinetic energy of all the molecules in a substance. So when temperature increases, you know that the kinetic energy of the molecules in that substance, they're also increasing. Now, kinetic energy is due to motion, but motion can either be from translational, it can be from one place to another, or it can be vibrational, like just molecules are moving, right? So as they move from here to here, back and forth, that's motion, and it's kinetic energy. So what's the difference between temperature and heat then? Well, temperature can be measured directly on a substance, and it can be assigned as a property of that substance. That's its temperature. But heat can only be measured when energy is transferred from one place to another. And the way we measure it is by using temperature. So they are related. But heat is actually a measure of the transfer of energy between two substances. And those substances have to be at different temperatures, because heat always flows downhill, we say, from a higher value of temperature to a lower value of temperature. Okay, so let's define what work is. A physical definition of work is a force. Let's see, I used a capital. I'm going to use a capital. Force that's applied through a distance. right? So what are the units of force in the SI system? The Newton. And what is the standard SI distance for, in the SI system, the distance is measured in meters. And work is in terms of energy. It's energy units, so it's joules. Okay, so that means that a joule is equal to a Newton meter. But the definition is that if you apply a force to something and it doesn't move, you haven't done any work. Now you still applied force, and in order to apply a force, you have to expend energy. Right? So I could stand there and push on the wall, and the wall won't move, but I am expending energy. So where does that energy go? It's converted into heat. Right? All that energy that's expended in the biochemical reactions in my cells and my muscles that are generating that force, rather than creating or being converted into work, a force applied to a distance, all of that value of force, the energy that's required to produce the force, is converted into heat. Now, it may be imperceptible. Like if I push on that wall, there'll be some heat, of course, in my muscles, but as I push on the wall, I'm moving some of those molecules, so they're heating up, but it's imperceptible. It's almost immeasurable. Okay, so in order to have work, the force has to act through a distance. Now I'm going to introduce another, a couple of more definitions, and they're useful because of what they require of you when you're trying to solve a problem. And it's the difference between a state function and a path function. Okay, these are both functions. Okay, what does a state function mean? A state function describes a property of something or a property of a process that does not depend in any way on the past or the future of the system. Whatever we define as our system, the state function says this is the way it is right now. I don't care what it was before, I don't care what it is in the future. This is it right now. And energy is a state function. It's independent of past or future. Whereas a path function depends on what happened in the past. How did you get here to where you are now? And heat is a path function, and we give it a small q letter. That's our value, that's our variable for heat. And it depends on where you were at the beginning and how you got to where you are now, right? So if I were to go up a mountain like this, a certain amount of energy would be required to go from this height to this height, right? From that position A to that position B. Energy is required. It only matters that I got from here and how high it is, right? Because it's a state function. Where am I now? What does that represent in some reference system? But if I go from here to here, and I have to expend, heat is transferred in the process. The engine in your car, it's often referred to as a heat engine, right? So as the gasoline burns, it produces heat, and the movement of heat from one place to another is used by the engine to create force and move your car forward doing work. So if we go straight up, a certain amount of heat is expended, right? But if we go like this on a twisty road, that requires a different amount of heat. So the path matters for heat. Okay, state function versus path function. Now there are other functions that can be classified in either category, and we'll encounter those as we proceed. We'll come back to those later. We need some more definitions. What is a system? I used that term just a few minutes ago. What is a system? You're gonna like this one. A system is anything you want it to be. And we define systems usually in terms of how best to solve a problem. So, but once you define what the system is, then that says everything else is surroundings. Right? So we define the universe in terms of the system we defined, and then on the universal scale, everything else in the universe is surroundings. Now, that's okay theoretically, but it's often useful to limit the extent of the surroundings. We can also define the surroundings too. So that's what this sort of rounded rectangle is for. That limits the surroundings to just this part of the universe. It's easier to deal with, actually, when you do calculations, to limit the surroundings as well as the system. Okay, so once we've got our system and our surroundings and we've boxed them in, like that, then we can define this arrangement as one of three different types. The first one is the open type. That's where energy and matter both can transfer between the system and the surroundings. There are no limitations on the movement. That has limited application, actually. But it is useful to recognize open systems because in nature, there are a lot of open systems. Okay, so the second one is where we restrict the movement of matter. We only let energy transfer, right? So we block matter and allow energy to transfer. That's a closed system. Open system, energy and matter can exchange. Closed system, only energy can exchange from one to the other. Now, in a laboratory setting, it's often more useful to use the third type, which is isolated system. That's a system in which we allow no transfer of energy or matter between the system and the surroundings. And one example of that, and I'll show it to you in just a second, is the calorimeter. I'm gonna have to define it for you too. But that isolated system allows no exchange. So whatever happens in Vegas stays in Vegas. Our system is Vegas. Everything that happens in here stays in here, and we don't care what's happening in the surroundings because matter, energy, neither one can transfer. This is an isolated system. And we try to establish an isolated system whenever we go on a picnic and we had cold beverages or things that need to be refrigerated, we put them in a cooler. And we try our very best to isolate that cooler from the 90-degree weather outside. It's not 100% efficient, but the attempt is there to create an isolated system in that cooler. Okay, those are our three types of systems. And now we can use that definition in terms of what type of reaction. We can characterize chemical reactions in terms of how the heat moves, right? So if the chemical reaction is endothermic, right? The reaction is our system, and it's got the surroundings, and we're letting energy transfer in this case. Then if heat flows into the system, then the reaction was endothermic. It's drawing energy from its surroundings. Whereas the converse, if the energy causes heat to move from the system to the surroundings, we have an exothermic reaction. And this may sound silly, but whenever that happens, when energy is transferred, the energy that's transferred from the surroundings, from the system to the surroundings, or from the surroundings to the system, the loss from one has to equal the gain to the other. In other words, there has to be a balance. And that goes back to can't create energy, can't destroy it, you can only transfer it. So it's sort of a budget, right? If the money is in your account and it's transferred to a creditor, then the creditor ideally gets the same amount of money that your account lost. Okay, so that's endothermic and exothermic reaction. Now, just as a hypothetical, what if our system is isolated and it's an exothermic reaction? We don't allow heat to transfer, right? So what's going to happen inside that system? Well, the temperature is going to rise, right? The heat's got to go somewhere. So it causes the temperature within the system in an isolated system to rise. Or if it's endothermic, the temperature will drop. And we use those measurements to describe the chemical reaction. And that's, I think, do we have one of those? I think we have one of those labs. Calorimetry lab. Yeah. Yeah, we have a calorimetry lab, and that's the concept. And I'm going to give you some more information, so don't try to jump on this horse and run with it yet. Okay, let's see if we understand what's happening. So, freezing of water. When we say freezing of water, what's our system? Well, the amount of water that we have in a container is the system. Right? So if the water freezes, which way is the energy traveling from the system? Right? If this is water and it freezes, how do you freeze something? You take energy out of it, don't you? You reduce its overall energy so that the molecules slow down, slow down, slow down. They finally get slow enough to where they solidify. So in order to do that, energy has to move out of the system, doesn't it? Actually, heat moves out of the system in order to freeze water. So defining the system, define the surroundings, right? And which way is the heat flowing? It's flowing out. So the process is exothermic. It may seem counterintuitive, right? The water's getting colder, so we're saying, oh, that's endothermic. Right? Endo means less than heat. So, but if we analyze the problem with this system surrounding scenario, then we decide that the process is actually exothermic. Heat is moving out of the system. And when we talk about the movement of heat, it's always relative to the system. Right? So if we're saying heat is moving out of the system, the sign, once we start quantifying that value, the sign is going to be positive. Negative. Duh. Negative. If heat moves into the system, which would be an endothermic, heat's moving in, that would be a positive Q. Relative to the system, we're adding heat to the system versus heat is being removed from the system, which would be negative. It's always in terms of the system, the sign of the quantity. Okay. The system is underlined in each one, so they've been kind enough to tell us what the system is. The system in this case, A, is your hand, and it gets cold when you touch ice. So what process is that? If your hand is the system and it's getting colder, that means heat's moving out of it. Exothermic, correct? How about ice gets warmer when you touch it? If ice is the system, it's gaining energy from your hand. It's endothermic. Water boils in a kettle. So we're adding heat to the water. Water's moving into the system, which is the water in the kettle. It has to be endothermic. How about this one? This might be a little more difficult to conceptualize. Water vapor condenses on a cold pipe. So it's not the water that's on the pipe. Well, actually it is, but it has to be water vapor first. So how do you condense water vapor? The same way you freeze ice, freeze water to ice. You take heat out of it. So you remove heat from the water vapor and it condenses, which means it's exothermic. Heat has to leave the water vapor. If the water vapor is the system, then heat's moving out, which is a negative value. It's exothermic. And ice cream melts. Let's see, to melt ice cream, you have to add heat to it. So it's endothermic. Okay, any questions about that? Okay. For each of the following, now we're going to have to define what is the system and what's the surroundings and give the direction of the energy transfer. So sometimes it's helpful to draw a picture. Right, so the first one, methane is burning in a Bunsen burner. Right, you all know what a Bunsen burner is now because you've done that lab. So our Bunsen burner is here and produces a flame, and it's a two-part flame, right? The inner and the outer. And which part is the hottest? Right at the tip of that inner cone. So, and there's our, to the gas valve. Okay, so, and we've got air control here, right? So methane is burning in a Bunsen burner, and natural gas is almost completely methane. There's some other things in it, but it's mostly methane. So as the methane is burning in the laboratory, what's the system? What's the surroundings? Well, I would say that the system is that flame. Right here. That's the system. That's where the reaction is occurring. So the surroundings would be the rest of the lab, right? And which way is the direction flowing? It's flowing from the system to the surroundings. So heat's moving this way, and the sign on the heat would be negative because it's moving out of the system. Leaving the system means it's negative and we're exothermic. Okay, Oops, sorry. Let's see, I gotta move that up out of the way so I can get to my controls down here. Come on. Let's see, where are they? There. I missed one. Water drops sitting on your skin after swimming, and they evaporate. So, what's the system? Well, in this case, look at it in terms of what is undergoing a transformation. And that is the water drops. Water drops sitting on my skin are evaporating. So we're going from liquid to gas. So if the water drops are the system, and as they evaporate, what are they doing? They need heat, right? You have to add energy to that water drop in order for it to evaporate. And where are the energy coming from? Well, some of it's coming from the air, but air is a pretty good insulator, actually. So most of the heat's coming from your hand. That means heat is going into the system, which is endothermic. And I don't think we have answers for this one on the slide. So we defined the water drops of the system, your skin is part of the surroundings, and heat transfer is into the system, endothermic. Okay. So hydrogen gas and oxygen gas react violently to form water, right? Anybody who's ever watched the space shuttle get launched into space, or some of the rockets that we are sending up now use hydrogen and oxygen. Hydrogen's the fuel, oxygen's the oxidizer. Mix them together, ignite them in the rocket engine, and it pushes your rocket up. But go back and look at some old, I know it's been a long time since the shuttle was launched into space. So you might have to go back and look at some old videos. But those three main engines on the back of the shuttle itself, not the two big boosters on the side, but just the three on the ass end of the space plane, are beneficiaries of hydrogen-oxygen reaction, and it produces a lot of energy. So, how do we explain that? Well, the mixture of hydrogen and oxygen is our system. And when they react, a lot of energy is given off to the surroundings, which is an exothermic reaction. But I might also make the point that what's left behind. In any rocket engine, you're taking advantage of Newton's third law of motion, which is every action is accompanied by an equal and opposite reaction. And the way the rocket engine works is that we accelerate the products of the reaction to a high velocity, which means lots of energy, and that action produces a reaction in the rocket, goes the opposite direction. So that's an open system, right? Because both matter and energy are being transferred to the surroundings. You're leaving that rocket gas behind. So that is a good example of an open system there. Okay. So now we're looking at the chemical reaction that takes place. And it's a very simple reaction that we write. Right. Hydrogen gas, oxygen gas, right? They're both diatomic. Never forget that. And they produce water, which is also a gas at those temperatures, right? So we balance it, right? We need 2 oxygens here which means we need 4 hydrogens. So there we've got a balanced equation, and we know that the reaction is exothermic. Right? So what does that mean to our reaction? If we're doing a Le Chatelier's thing, like we did before, what would the heat be? It would be a product, would it not? So there's our heat. So that describes the reaction. Now, when we do it that way, that also allows us to make some statements about the energy content of the reactants versus the products. So, in this case, which one, reactants altogether, or products, and this we're talking about the physical product, which one contains more potential energy? The reactants together have more potential energy than the products because it's an exothermic reaction, and here's the energy that used to be in here. Right? We have to balance. Everything has to balance, not just mass, but energy as well. So if we've got exothermic energy out this end, it had to be over here, buried in these reactants. So that means the reactants are at a higher energy state than the products. And we could draw that like this on our energy graph. All right, so here are the reactants. Here are the products. And here's the difference in energy. This also illustrates the negative nature of the value that we assign to energy, the heat that's transferred out of the system, right? We go from here to here, it's a negative difference, right? We're going downhill. So it's negative, and negative is exothermic. Okay. So in this case, water has the lower energy. All right, so I've already mentioned thermodynamics a little earlier. This is just reinforcement. When we study energy and its interconversions, we call that thermodynamics. And thermodynamics can be, it doesn't have to be chemical. It can be anything. It can be purely physical. And the law of conservation of energy is a statement of the first law of thermodynamics. And often in an equation form, we say the total change of energy in the universe is always 0. In other words, there is no change in the energy for the universe. All systems, all surroundings, everything together is 0. Now, we can define a term for our system, and we call it internal energy. And for theoretical purposes, we can just assign the large letter E for the internal energy of the system. It has a certain internal energy. As a practical matter, we don't know what that is unless we allow the energy to move. If we allow the energy to move and work to be done, then we can define a change in the internal energy of the system. So if we've got our system, theoretically we can say it has a certain amount of internal energy, but it's not measurable, not until it moves. And it's an expression of the total potential energy and kinetic energy of all the matter in that system. Right? So this is an expression of the potential energy and the kinetic energy, both, within that system. So how do we cause a change in the internal energy of the system? The change in the internal energy of the system can be affected, that's affected with an E, effected, can be affected with either a transfer of heat in or out of the system, or you can do work on the system or allow the system to do work on the surroundings, right? And remember what work is force applied through a distance. So you can either transfer heat or do work, and that will change the internal energy of the system. So heat's, we have a reasonable idea of what heat means, transfer in and out. But what do we mean by work? How do you do work on a system? If you're going to apply a force through a distance, I guess you could do that with a liquid or a solid. But if you do it with a solid, it's a little more difficult, because once you've defined the system, all you can do is move the whole system, right? So to keep things simpler and to derive our equations that are later useful for liquids and solids, we start with gases. So I'll just, as an aside, say that's why I introduce gases as early as possible in general chemistry, because so much is done with gases that is transferable to other states of matter. You have to have gases. I can't imagine, and I know of cases where chemistry is taught where the gases come toward the end. And by my way of thinking, that's ludicrous. Okay, I'm down off my soapbox now. Let's go to the next slide.
The first law of thermodynamics gives the relationship between the internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters and work is done by the system. Internal energy remains constant if there is no friction. If instead of adding heat, we do work on the system by compressing the piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
So in order to answer that question, was there a change in internal energy? We look at the signs, right? At the beginning of that little video, these two were being balanced. In other words, as heat was moving in, work was leaving the system because the system was doing work on its surroundings. So if this was positive and this is negative, but they're both the same magnitude, then they cancel one another out. And you can go the other direction. You can do work on the system and then allow heat to transfer out of the system. Then the change in internal energy would be zero, because these both balance one another. But in this other example where we have, let's see.
The first law of thermodynamics.
Over to here, where we have zinc and hydrochloric acid are reacting. So potential energy, chemical potential energy is releasing heat. Let's see if I can step it up a little bit. Okay. So if we allow heat to leave the system and And the internal energy of that system was the summation of both the kinetic and potential energy, right? So it's not like we're creating more energy by the chemical reaction. It has a certain amount of internal energy due to its potential primarily. So now with the chemical reaction, what's happening? Well, the system is doing work on its surroundings, which means negative, right? Work is leaving the system, and heat is leaving the system as well. So it's negative. That means that the internal energy of the system is decreasing because it's losing work and heat. Okay, does everybody see that?
Signs on Q and W in this example. Is there a change in internal energy?
Yes, they're both negative. That means the change in energy is, internal energy is negative. That means it's going down within the system. Okay. So this is just to hammer the point home again. For internal energy and for any thermodynamic quantities, the two important parts, my way of thinking, there are three actually. You got the number or the magnitude of the change, and you have the sign of the change. Which way is it moving? And then the third one that I'm thinking of is units of measure, right? I mean, if you don't have the units of measure, you can't compare the energy here with energy happening anywhere else. My way of thinking is they just assumed that the energy units are joules, right? And they're always going to be joules. But what if they're kilojoules? Right? So you actually have three considerations: the sign on the number itself, and the units of measure. You're probably wondering, why didn't I change the slide before I got to that part? I missed that one. Okay. So this is just, I've already given you this one. This is a slide just saying the sign on that number always reflects the system's perspective. What does the system see? Something coming in, positive. Something going out, negative. And it's the same for heat and work. Although work takes a little thinking, you know, okay, the system does work on the surroundings. So for a gas, that means the gas is expanding, say, inside the system, but in the process, it's applying a force to its surroundings. So as long as it moves through a distance with that force, work is being done. Force times distance. Now this, I'm going to show you a derivation. You have to know how to do this. This just proves the point that there is relationship between the way a gas behaves, expands or contracts, and work that's being done. So what we have a piston here in a cylinder of uniform diameter, and there's no friction. Right? We're not going to lose any energy to friction. That's a hypothetical. So this piston is under pressure, right? And pressure is an intrinsic value, a property, which means in this case it's a force per unit area, right? So the pressure is the same all over that cylinder, and it's represented by force per unit area. Okay, if we allow the gas to expand under that constant pressure, then what's happened? We have a change in height of the piston, and since the cylinder is uniform diameter, we can calculate a change in volume. So that's what this is doing. Take a height, change in height times the area gives you a change in volume, right? So we've got that much as part of our calculation. We've changed the volume under a constant pressure. So force acting over a distance is work, right? So pressure equals force divided by area. Rearrange the equation. There's your force, pressure times area. So we could substitute force as pressure times area into that F value. Oh, but first we want to define what, excuse me. We have to define the two. So there's force, and here's a change in volume, which is the diameter of the cylinder times its area. So the diameter, no, distance, excuse me. D is distance times area is here. So now we've got two substitutions. We've got force here and area here. So now we make the substitutions for both of them. And we have this expression. There's our force, there's our distance, and A is in the numerator here, the denominator there, A cancels, and leaves us with work equals pressure times change in volume. That's another expression for work, and this is particular for a gas that is either expanding or contracting. Okay, so there we have work equals pressure times the change in volume. The problem is the convention for expressing work, in this case, work is being done by the gas on its surroundings, which means work is leaving the system. So work has to be a negative value. But look, pressure is a constant positive value, and a change in distance was positive, and the area is positive. So P times delta V is a positive number. So it can't be equal to W with our present convention. So that's why we stick this negative sign in front of it, so that the not only the units of measure, but the signs match. So a negative P delta V is equal to the work. Now, if you have to convert pressure times volume units, right? Pressure in atmospheres, volume in liters, into joules, you need to use this equivalence, right? Because if you only use liter and atmospheres over here, then work is in terms of liter atmospheres. But if you need to express it in terms of joules, you've got to convert liter atmospheres to joules. And there you have an equivalence, right? This is equal to that, so you can make a conversion factor out of that. Just decide which one needs to cancel. That tells you which one goes on top, which one goes on the bottom. Okay, let's see. Oh, I don't have my copy out, so I'm not sure where a good place to stop is. I'll just run up to 45 minutes, hour and 45 minutes, and we'll stop there. Yeah, I need to know, because I got to make a note. So, had to move a cat. Okay, here's my hard copy. And let's see. Here we go. Okay, we're about halfway. So this, another couple of slides, and it'll be a convenient time to stop. So that works out pretty well. Okay, so which of the following performs more work? A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. Okay. So let's do the calculation. So now we're just dealing with the work term. We're not looking at the heat, just the work. So W equals negative constant pressure times the change in volume. All right. So constant pressure is 2 atmospheres for A. With our negative sign. And a change in volume is what? Final volume minus initial volume. So initial volume is 1, final volume is 4. That means it's 4 minus 1 liters. Right? So this is a positive 3, a positive 2, gives you 6 liter atmospheres. Right? So that's A, 6 liter atmospheres. B, W is a negative 6 liter atmospheres, right? We're expanding a gas against a pressure from 1 to 4. So that means work is being done on the surroundings. Think of that. As a gas expands, it does work on the surroundings. So this one is a negative 3 atmospheres. And what's the change in volume? 1 to 3. So the final is 3 minus 1 initial. That's 2. 2 times 3 is 6. They're exactly the same amount of work was done on the system, on the surroundings. Okay? All right, so let's do this one, and I think that'll be a convenient, that'll be a convenient stopping place. So we'll do this slide. And this will be the end of part 1 for chapter 6 on thermochemistry. All right, determine the sign of delta E for each of the following with the listed conditions. The best way to do these kind is Henry Ford. Just set up an assembly line. So if we're interested in the sign on delta E, right, and we're given these conditions for A, and the first one is work. It's an endothermic process. All right, so I need to move that. Endothermic. Let me put this over here. Way over here. That's our answer. So these are the conditions. Work, the absolute value. See those 2 bars? That means absolute value. It means if it's a positive, leave it alone. If it's a negative, drop the negative. We're only concerned with the magnitude of the value. If the magnitude of work is greater than heat in an endothermic process. So with endothermic process, an endothermic process that performs work. Performs work, what? What does that mean? It means performs work on the surroundings, right? So if it performs work on the surroundings, that means the value of W is what? If it performs work on the surroundings, the value of W is negative. And if it's endothermic, the sign on Q is positive. Okay, that's what endothermic means. And then work on the system, work on the surroundings is negative. Okay, now we look at the absolute values for work and heat. So if the absolute value of W is greater than heat, what's the sign on this one? All right, so in this case, if this one is bigger than that one, then this would be negative, right? And vice versa, if this is less than that, change in internal energy would be positive. Okay, What about this one for the exothermic? Okay, we have exothermic process, and work is done on the gas, which means now this is going to be negative exothermic, and positive work is done on the gas. So now if we have W greater than Q, then this one is greater than that one, means this is positive. And vice versa, if Q is greater than W, that one's greater than this one, that means negative wins. Okay? So this is not something that you can just churn around in your head and answer. You got to think about it. What is the problem saying? What are the conditions, and what is it asking? So this way we get the conditions here and here. Then we can figure out the sign on delta E. Let's just check to be sure I got them right. Okay. All right. So when we pick this up Thursday, we'll introduce the concept of enthalpy. So it might do well for you to read the chapter ahead of time. Let me make a note for myself, and if anybody has any, let me unshare this, stop the share. Anybody has any questions before I depart?